So I wanted to look at a few things about the Danielle cell that we set up for the Gibbs Free Energy Lab before we start looking at how to do the math. For one, I just took the standard reduction potentials from the chart for the two half cells that we're looking at. We have the zinc half cell, which has a standard potential of negative 0.762 volts, and the copper half cell, which has a cell potential of 3.340 volts. We know overall that this cell potential is equal to this potential of the cathode minus the potential of the anode, and since this was a galvanic cell, E0 has to be positive. One way to tell where my cathode is if I have the reduction potential table is to find the most positive value. Now 0.34 is not very big, but it is much more positive than a negative 0.762. So the positive reduction potential here is my cathode. Then I subtract the reduction potential of my anode, remembering that subtracting a negative number is equivalent to adding. And I get E0 here is 1.10 volts. So looking at this, I'd also like to just look at what's going on and what kind of products and reactants am I dealing with so that I can write a K expression. Well, the copper reduction at the cathode, I can just leave that the way it was in the table because they're all reduction potentials. For the zinc, however, that's my oxidation. Oxidation is losing electrons. So I'm going to have to flip that to look at what the products are of my oxidation reaction. So this turns out to be a pretty easy equilibrium constant to write because there are no solids in K. So we just have our product ion, the concentration of zinc, over the reactant ion, the concentration of copper 2+. No solids in the K. So we're going to use these cell potential values that we calculated to start looking at the Gibbs free energy. The equation for Gibbs free energy is fairly simple. Delta G is equal to minus NFE. So let's unpack that a little. N is the number of moles of electrons per mole of reaction. So in our case, we have zinc becoming zinc 2+, copper 2+ becoming copper, so we're transferring 2 moles of electrons per mole of reaction. F is the Faraday constant. It's actually the charge in coulombs per 1 mole of electrons. On the formula sheet, you'll see that is 96,485 coulombs per mole of electrons. Sometimes you'll see people use 96,500, but I'm going to use the value you'll find on the formula sheet. And of course, E is the cell voltage, what we measured in the lab. Do make sure and notice it is minus NFE, it is negative NFE. That's going to be really, really important. So looking at a data set from the lab today, we had a really nice linear data set from a group today. And Logger Pro is good at math, so I'm going to take advantage of that and have it do some calculations. So I'm going to go to Data, and I'm going to get a new calculated column. Now, one thing I know is that when I'm doing some of these calculations later, I'm going to need the temperature in Kelvin. So the first thing I'm going to do, just so I have that, is I'm going to do the Kelvin temperature. Of course, the short name there would be T, and the units are in K. So that's a fairly simple thing to put in. We go to the expression, we go to variables, click temperature, and then we know to convert to Kelvin temperature, we add 273.15. And we'll click done here. And now we have our green column here that has our Kelvin temperatures. So we want to do the Gibbs free energy. Again, we'll go up to data and we'll get a new calculated column. Call that the Gibbs free energy. And Logger Pro can actually do that really nicely. If we go to our short name, there's a drop down here, and we can get a Greek capital letter delta to make a delta G. And in this case, it's going to be in units of joules per mole. So to get the expression, remember it's minus NFE. So negative, N we said is 2 moles of electrons, times the Faraday constant, 96485, times the cell potential. Well, that's what we measured. So you go to columns and click potential to get the cell potential. And when you click done, you're going to get a big column, and for a second it's going to look kind of strange. If you spread that out a little bit, you can see that those are actually negative numbers. So now I have the Gibbs free energy for each point. The next thing that it said it wanted you to calculate was the standard Gibbs free energy at each point. Well, the standard Gibbs free energy is given by the Gibbs free energy you calculate, minus R, that's that 8.314 joules per kmol, times the temperature in Kelvin, times the natural log of the reaction quotient, Q. Well, remember, a reaction quotient looks just like the equilibrium constant, so it's going to be the concentration of zinc divided by the concentration of copper ions. And both of those are 1 molar solutions. And we didn't run the battery very long, so they probably stayed essentially 1 molar solutions. So we'll come back to here, we'll go up to data, and we'll get another new calculated column. This time we can call it standard Gibbs free energy. And again, we can go down here to our short name, and we can actually use Logger Pro to get that too. We can get a Greek upper for the delta, G, and then the standard has the degree sign to denote that that is the standard. So we can find that under the drop down as well. Again, this will be in joules per mole. So now with this expression, it's a little more complicated to type in. It's going to start with the variable, the Gibbs free energy that we calculated. And we know that's minus RT ln Q. So open up a parentheses. You're going to type in R, 8.314, times, oh, we need the temperature. Well, we have the Kelvin temperature, so click on variables and go down to Kelvin temperature. Make sure you're using the Kelvin temperature, times, and to find the natural log, we have to go to functions. You see it's right about the middle of the column, ln, and we have 1.0 molar zinc and 1.0 molar copper 2+. Close that parentheses to make sure that that whole term is going to work. So click done. And you'll notice something kind of interesting here. Those two numbers are exactly the same. Well, if you think about it, you took the natural log of 1, and the natural log of 1 is 0. So it really didn't matter what temperature we were working at, because we were using standard concentrations, we had 1 as our Q. Okay, well, now that I have delta G0 at these different temperatures, I'm going to want to use that to find the other values in my lab report. Well, one way to do that is to find the trend, because I don't have delta G specifically at 25 degrees at standard temperature. I have it at 27, I have it at 17, but I don't have it exactly at 25. So in order to find that exactly at 25, we can use the graph. and the linear equation. So go up to Insert, click Graph, and it's going to give you a graph of standard Gibbs free energy. Hopefully that'll be the last thing you calculated. And we don't want it against event number. We want it against the temperature. And you'll see that's not a great looking graph, so I'm going to go ahead and auto scale that. Use the big A up on the corner. And now I have an auto scaled graph. And I can use the linear fit tool to find a slope here. So now I have everything I need to get the linear equation. I'm going to write down the slope and the y-intercept here, remembering that that is a 10 to the 5th E plus 0.005. That's 10 to the 5th joules per mole. So what am I going to do now that I have this linear equation? Well, when I have the linear equation, I can set this up, and I want to solve that for the standard temperature at 298 K so that I can get G0 at 298. Once I have G0, then I can use that in my same Gibbs free energy equation from earlier to solve for E0 at 298, and I will calculate the percent error in my cell voltage. Don't be too concerned about the number, but make sure you use it. The other thing I can do now with this solution from my linear equation is to use that to solve for KEQ, and that uses delta G equals RATLink, RT ln of K, to solve for KEQ. Remember, if I'm trying to solve for natural log of K, I'm going to have to take everything E to that power so that I can get rid of that natural log. Then you have a couple other questions to talk about. What is the Faraday's constant? What do the sign of delta G tell you, and is that surprising? But answer those questions and you should be all done.